Let us discuss the situation when multiple dielectric slabs are there in a single capacitor. Here in this situation you can see between a capacitor having plate separation given as D. In this plate separation D, there are three dielectric slabs which are inserted parallel to each other, which are having thicknesses T1, T2 and T3. Now in this situation, if the dielectric slabs are completely filling the space and if we wish to find out the capacitance of the system, this can be regarded as a system of three capacitors placed one after another in series. We can treat this system as a single capacitor having dielectric constant K1. It can be separated like this. It is C1. And the capacitance C1 we can write as K1 epsilon naught A by T1. Because if we insert a negligible thickness metal plate here, this will become a dielectric K1 which is inserted in a capacitor having plate separation T1. Then this second slab can be treated as another capacitor between two plates having separation T2 between them, and a dielectric slab K2 is filling the space. If we just separate the two with a conducting wire, this will become a capacitor C2, and here C2 can be written as K2 epsilon naught A by T2. Similarly, this third one can be further separated as this is the second capacitor, this is the third capacitor, which is further connected in series between the last plate of capacitor and the middle plate, separated by a separation T3. Then C3 we can write as K3 epsilon naught A by T3. Now in this situation, as the three capacitor can be regarded in series combination between terminals A and B, so we can simply write the equivalent capacitance of the system. Here, say we study the whole analysis under case 1 when slabs of dielectric are parallel to capacitor plates. Here you can see in this situation dielectric slabs are inserted parallel to plates of capacitor. In this situation we can write 1 upon CAB, that is the capacitance of this whole system. It can be written as 1 by C1 plus 1 by C2 plus 1 by C3 because these three capacitors are regarded in series combination, which is making the whole system. So we substitute the values of C1, C2, C3 here. You can see this will give us 1 upon K1 epsilon naught A by T1 plus 1 upon K2 epsilon naught A by T2 plus 1 upon K3 epsilon naught A by T3. We just simplify the expression and take its reciprocal. We get the final capacitance of the system we are looking for. This can be given as epsilon naught A upon T1 by K1 plus T2 by K2 plus T3 by K3. This is the way how we can calculate it, and for any number of plates, or we can say for n slabs of dielectric, we can calculate the value of equivalent capacitance of such a system as given by epsilon naught A divided by T1 by K1 plus T2 by K2 plus and so on up to Tn by K. And this is the way how we can calculate the equivalent capacitance of such a system in which there are n dielectric slabs placed parallel to each other, completely fills the space between the plates of the capacitor. Let's discuss the case 2 of multiple dielectric slabs in a parallel plate capacitor. Here you can see a situation in which in a capacitor of terminals A and B, three dielectric slabs are again inserted, but now the slabs of dielectric are perpendicular to the plates of capacitor. In this situation, we can see that across all three plates, the potential difference remains same because K1, K2, K3, all three dielectrics are connected, one side with the plate which is at terminal A and other side with the plate which is at terminal B. So here if we split the three dielectric slabs, then we can Consider it as a system of three capacitors C1, C2, C3 in parallel combination, because the three plates of three dielectrics are connected with the terminal A and the other three plates of the three capacitors are connected with the terminal B. Now even if we join all these side by side, it will be in a situation like this, and the potential difference of all three capacitors will remain same. So in this situation we can say the capacitance of system across terminals A and B in presence of the three slabs can be written as C1 plus C2 plus C3, because the three capacitors are considered to be in parallel combination. And here the values of C1, C2, C3 can be obtained as C1 we can write as, here we can see in all three capacitors the plate separation will remain same as D, but the plate area will differ. As the total plate area is LB if L is the length, so in this situation B is the width of the capacitor plate. So for each capacitor we can find out the plate area to be length multiplied by the width. So for this capacitor C1 the plate area will be X1B. So it can be written as K1 epsilon naught X1B by D. Similarly C2 we can write K2 epsilon naught X2B by D. This is epsilon naught A by D multiplied by the dielectric constant. And C3 we can write K3 epsilon naught X3B by D. Now from here if we just calculate the value of CAB, you can see in the situation we are getting, after adding all these three, this will be epsilon naught B by D multiplied by K1 X1 plus K2 X2 plus K3 X3. This is the relation we use for the capacitance which we were looking for in presence of three dielectric slabs completely filling the space between the two plates of a capacitor. Similarly, you can generalize the expression for n slabs as equivalent capacitance we can write as epsilon naught B by D, where D is the plate separation and B is the width of the plates, multiplied by K1 X1 plus K2 X2 plus up to KNXN we can use. Be careful about these relations which are used for multiple dielectric slabs in a capacitor.